All right, so chapter 16 is going to talk about really thermodynamics in this chapter. So it's a little bit different than some of the stuff that we talked about previously, but not so much because you see equilibrium up there, which means we're going to actually use some of the other letters in the alphabet, surprisingly. So we're going to talk about entropy, which is our friend delta S, and we'll talk about free energy, which is our friend delta G. We'll also visit a friend from the past of delta H, which is our enthalpy. And of course, this class cannot be brought to you without revisiting K there at some point along the way. So we will see all the letters of the alphabet here. So we're going to continue on with our talk of thermodynamics, sort of a continuation of some of the stuff that you did in Chem 50. You did sort of the energy part of thermodynamics, which is sort of the first law of thermodynamics, which is the conservation of energy. So we're going to kind of build on that and look at some of these other thermodynamic sort of properties. Remember that when we talk about thermodynamics, really the question sort of what a lot of things that we're looking at is whether or not a reaction is going to be spontaneous. So a reminder that if a reaction is spontaneous, sometimes people have a misunderstanding of that word. Sometimes they associate that word with it happening very fast, like it's going to snap your fingers and happen spontaneously. And that's not necessarily what spontaneous means. In this case, spontaneous means in this case that under those conditions, you would expect this reaction to actually take place. And it could be really fast. It could be really slow. There's a lot of spontaneous reactions that are super slow, but they do take place. And there's a lot of ones that are very, very fast. So remember that when we talk about sort of how fast or slow a reaction takes place, that's the kinetic stuff that we talked about at the very beginning of the class. But here, we're mainly focused on that idea a lot of times of spontaneity. And again, that just basically emphasizes that under those particular conditions, we would expect, this reaction to take place. So there's a lot of spontaneous physical and chemical processes that we may be aware of here. Water flows downhill. If it goes the other way, maybe something's weird. A lump of water dissolves in a cup of coffee. 1 atmosphere at 0 degrees, we'll get water that freezes. Heat flows from hotter objects to cooler objects, right? So that's always the flow of sort of heat. The hot object gets cooler object gets warmer. If they kind of meet maybe somewhere there in the middle. Iron exposed to oxygen, a little bit of moisture is pretty much all you need for rust. The person is skiing down the hill, gonna be spontaneous. Guy coming up the hill, gonna be non-spontaneous, gonna have to do a little work to do that, probably freaking this guy out. I'm imagining that's not what you want to see as he comes down the hill, somebody coming up the other way. But that's obviously a non-spontaneous process. You can stand at the bottom of the hill all day, you're not going to get yourself up to the top, right? Without something happening to help you get there. Obviously, if you're at the top of the hill, you just go over the hill. I'll get you going down the hill pretty quick. So a couple other things that are spontaneous. If we have sort of gas molecules separated by a little container there, and you could open the sort of valve, spontaneously, these guys will kind of flow into the open space there. Non-spontaneous event would be if we did have guys on both sides here, they wouldn't probably automatically all just kind of end up on one side without a little convincing to get them over to that particular side. So does a decrease in enthalpy mean that a reaction proceeds spontaneously? A reminder that enthalpy, or the change in enthalpy, right, is our delta H. And when we do have a negative value, that is a exothermic process where heat and energy is released. When we have a positive value, that is a endothermic process. Where heat and energy is absorbed, right? So energy released, energy absorbed here. And as you probably know, one way to calculate, right, your delta H of your reaction is to do the delta H of your products, right, minus the delta H of your reactants. You take all of the delta H values for your products and you subtract it from all the delta H values from your reactants, and I'll give you the delta H overall for the reaction. So here are some spontaneous reactions. We've got a combustion reaction. We have the formation of water, each of which are exothermic as they have a negative value here for our delta H's. We have the melting here of ice, and that is an endothermic process. That's the heat of fusion to do that. And here making a solution here, it's also endothermic. So these are all processes that occur, and you can see the value of delta H, or the value of the enthalpy, is not really the determining factor in terms of whether or not a reaction will be spontaneous or not, since you got a little bit of both happening there, right? You got some positive delta H's, some negative delta H's. So although an exothermic reaction does sort of favor spontaneity, in order for it to be exothermic, energy has to be released, some excess energy. That's going to be very helpful for everything to start reacting and coming together. It does not necessarily guarantee it. So we do have to look at sort of another sort of factor to help us decide whether or not a reaction will be spontaneous. And that factor is our friend entropy, which should not be confused with enthalpy, which sounds very similar. So entropy, or the change in entropy, which is delta S, is the amount of randomness or disorder there is in a system. So when we have a lot more order or less disorder, whichever way you want to think about it, I suppose, we have actually a more negative value for delta S. So when we really get things more organized and ordered, we're actually decreasing the entropy of that system, because entropy is the amount of disorder and randomness that's happening. So when you put things in order, that kind of makes that not so great. When we actually increase the disorder, which would be decreasing the order, we actually see a more positive value for delta S. So that's a little bit different. Sometimes we think about enthalpy and negative being exothermic and things happening, but actually here with entropy, delta S, the more disorder and craziness that you have, the more positive of a value of delta S you're going to end up with, and vice versa. The more organized things are, the less disorder that you have, you're going to have a more negative value of delta S. So if the final state increases the amount of randomness, we would expect, again, a more positive value. And if we kind of are creating more order, a more negative value. Very common way to kind of see that is with the changes of state. So solid guys are pretty much packed in there, pretty organized, right? So that's a very ordered sort of state. When we get to liquid, there's a little bit more room for movement, so things start to move around. So obviously there's more disorder that's happening. When we get to gas, everybody's apart from each other. They're flying around crazily in the container. So there's a lot of disorder that's happening. So things in their gas state have a larger entropy value, a more positive entropy value than, say, a liquid, and a liquid would have more entropy than a solid state. So a lot of times in the thermodynamics chapter, they oftentimes will ask you to do some predictions, for example, without even doing calculations, just sort of based on the equation and what is happening. So for here, we're going from solid to liquid. So again, we're going from a really more ordered sort of situation into a situation where there's a little bit more room for movement. That's going to create more disorder here. So we would expect a positive delta S in this case, because of that, because we are increasing the disorder here. Our delta S would be greater than 0. Any questions on that? So entropy is one factor that we could use, as we'll talk about here, to again determine, whether or not a reaction is going to be spontaneous. There's a couple of different sort of entropy values that we need to sort of look at to help us make that decision. So disorder is related to probability. And when we talk about probability, a probable event is one that can happen in many ways. An improbable event is one where there's only a few ways for it to occur. For example, a probable event would be if we needed to get out of a room that had like 6 doors. You could pretty much get out of the room, no problem, right? Pick a door, you get out. Pretty probable everybody's gonna get out. We're in a room with no doors and a very small opening window at the very top corner of the room. That's a little bit more difficult now in that case. Perhaps it's going to be a little bit more improbable that we get out of the room. These are cheerful thoughts as we lecture here today. So The other idea there is, if you think about it, you know, there's many ways you could screw up. Yes. Only a few ways you could do something right, right? So there is a high probability of messing up sometimes, and to do something correctly is sort of a low probability of happening. So a very ordered state means that everybody needs to really come together in a very ordered and organized fashion. So there's a low probability of that occurring, and a small entropy, much greater chance of, you know, things having a much bigger disordered state and a bigger probability of that occurring. One way we could relate entropy to sort of probability is what is referred to here sometimes the Boltzmann constant or Boltzmann equation. This is the entropy. K is the Boltzmann constant, which is on the bottom there. And that is W, which is the number of microstates. Microstates is basically the number of ways you could do something, pretty much. So for example, here, if we had 4 circles and we wanted to put all 4 circles on in one box, there's really only one way that you can essentially do that. And that would either be on the left-hand side or the right-hand side, basically. If we wanted to put 1 circle in one box and 3 in the other, there's 4 different ways that you could achieve that. And if you wanted to just put 2 circles in each box, there's 6 different ways of doing that. Like the old carnival game, you want to shoot all 4 basketballs in the one side. A lot harder, right, than just having to lay up 2 on one side versus the other, depending on your skill level. I understand it's all right. But so when we look at this, there's a greater sort of probability or a greater entropy going to happen here when we have many more microstates. We look at the Boltzmann equation and then just frankly put in here our W of 1. That's going to give us S is equal to K natural log of 1. Natural log of 1 is equal to 0, right? And so very low entropy value in that case. If we do it for our other guy there, natural log of 6 is like 1.79 times K is equal to S. So obviously a much larger entropy value you would achieve for that, since the Boltzmann constant is the same in each case. So the greater the microstates, the greater the ways that you could do something, probably the higher the entropy value is going to be. Again, the less ways that you could achieve something, the smaller the entropy value is going to end up being. Again, these are a few processes where we do see an increase in the entropy when we go from solid to liquid. Again, that solid very organized into our liquid, a little bit more room for movement. Liquid into gas phase, also more room for movement. When we make a solution, that increases the entropy for both parts of a solution. The solvent, before you dissolve it, is all bonded together like hydrogen bonding in water, so a nice organized sort of situation. And your solute is hanging here together in your positive negative electrostatic attraction and ionic solid, which is a very organized sort of situation. In order for both of those guys to dissolve, you got to kind of break everybody apart and start inserting some of those ions into the water network, creating a lot more disorder than you had when you started. Same thing with temperature, right? The old saying, if you light a fire under somebody, it's going to start moving faster. Same idea here. If we increase the temperature, everybody's going to have more energy, which means, for example, if they're gases, they're going to be flying around a lot faster, right? And things of that nature. And even in sort of the solution phase, more energy is going to get everybody kind of moving around a lot faster than they would at a lower temperature. So these are all situations where we would expect the delta S to be positive. Questions on that there? By the way, when we talk about thermodynamics, there's a couple sort of things that we do talk about, and that is the system, right? And basically the surroundings. So the system is pretty much whatever you are looking at, whatever you are working with. And that could be a test tube, could be a beaker, whatever it may be. And pretty much surroundings is everything outside of that. So a lot of times in thermodynamics, where we look at either the flow from the system to the surroundings, or the flow of this from the surroundings back to the system. as you might remember from something like heat and energy, right? There's sort of a perfect, like delta H, for example, it's kind of a perfect exchange of that, right? However much energy somebody loses, for example, if the system loses negative 115 kilojoules of energy, the surroundings is going to basically gain that, right? And so it's basically the sort of equal amount going in and out of the system, depending on which way you are going in this case. Once again, a negative value for energy implies exothermic releasing that energy, and a positive value meaning that it's going to be gaining it. So for these different processes here, decide how does the change in entropy of the system changes? Does it increase, decrease? Would we expect a positive or negative value? Okay, so let's take a look at this. So condensing water vapor, that is condensation, which means you are going from gas back to liquid, I believe. And that is definitely going to create more order, right? So instead of gas molecules where everybody's flying around, everybody kind of slowed down and went into the liquid phase there. So that would definitely increase the order. And that means we should actually see a decrease in the entropy, and the delta S should be negative in this case. So again, when we create more order, we will end up with a delta S that is negative. Forming sucrose crystals from a supersaturated solution. Sucrose crystals is a solid, and a crystal is a fairly organized sort of entity. So that's going to also increase the order, which should decrease the entropy, and our delta S here should be negative. When we heat hydrogen gas from 60 to 80 degrees, we're increasing the temperature, which means our gas molecules now should be flying around a lot faster, right? And that obviously, just visualize it flying around your face, right? A lot faster. That's going to create a lot more disorder, right? So that's going to increase the disorder. And that means that the entropy will actually increase, and we'll end up with a more positive value there for our delta S. Lastly, sublimation here, going from not that solid as I just mentioned, directly to gas. Again, skipping the liquid hassle. In that case, obviously, we're going from a more ordered situation to a situation where everybody is flying around. So that's going to increase, again, a lot more disorder, and increase in the disorder, increase in the entropy, and we should end up with a positive value here for our delta S. Any questions on any of those there? Okay, so let's talk a little bit about entropy a little bit closer. Entropy is a state function, and if you remember what state functions are, they are state functions. So they does not matter how you get there, just get there if you can. That is a song, you can look it up. All right, so what does matter though is basically where you start and where you end are the only two places that really matter. As we can see here, the guy in blue there took the more direct route up the mountain. The red one here had a longer period of time, so he took the scenic route around the mountain. But in terms of their potential energy, they both basically started and ended in the same spots, which means they do possess the same potential energy. So this is why in a lot of cases we do things like final minus initial, right? And that is because in a chemical reaction, when we take our reactants to our products, that is our initial state, that is our final state. So that's why we take products minus reactants in a lot of these things that we calculate, because that will give us our final minus our initial sort of situation in this case. So when we look at entropy, one way that you could calculate the change in entropy is to take the entropy value of your products minus the entropy value of your reactants. This is also the idea behind, as you might remember, Hess's law, where you could add up all those individual equations to get an overall equation. It doesn't matter if it takes you 32 steps or 2 steps. At the end, in terms of energy, it's just the sum of everything that's happening, where you started and where you end. Now, when we look up entropy values in a table like this one, a couple things are different than, say, a delta H table that you may look up. And first off, it is the units. So typically speaking, delta H is in units of kilojoules. And typically speaking, as you can see here, delta S is typically given in joules. And that's going to be a problem a little bit later on, because we will use both of those values together in some formulas. So you want to make sure unit-wise everybody's in the correct units and you're not off by a factor of 1,000. Also different is delta S values that you look up in a table are essentially all going to be positive values. So you won't probably find any too much negative values there for your entropy sort of values in this particular table. When I look up a delta H value, by the way, for something like O2 or like H2, those values are 0 kilojoules, right? They have a value of 0. But for entropy, you will actually find values for those things in here. So that's a little bit different than like a delta H table. You'll actually see values for things in their standard state, which is different than what you typically would see with a delta H table. As you're probably familiar with, when you go to these type of tables, a couple of things you also want to make sure of. You want to make sure you not only find the thing that you're looking for, but you do find it in the correct state. So if it's gas, it's aqueous, if it's solid, whatever it may be, you want to make sure you just grab the right one in the right state, not just the first one you find on the table. So very common, like water, people just like grab the first one, but it may be in the gas state versus liquid or something like that. So you want to watch out for those type of things as well. Little kind of knot there means usually standard sort of conditions and the table type conditions. And when we talk about table type conditions, usually that means a temperature of like 25 degrees Celsius, a pressure of 1 atmosphere if you're dealing with gases, a molarity of 1 molar. So these are sort of standard sort of table sort of situations or conditions. And that's usually what the little knot means, is it's being done under sort of standard conditions, under those type of conditions when you do it. Any questions on that? So the first law of thermodynamics, as we mentioned, is the energy component of it. And again, that is energy can be converted from one form to another, but cannot be created nor destroyed. So we think about energy, again, being transferred sort of perfectly. Whatever somebody loses should be the same amount of energy that somebody gained. The second law of thermodynamics is the world is crazy and entropy is increasing. The entropy of the universe is increasing in a spontaneous process and remains unchanged in an equilibrium process. And that's because in an equilibrium process, it has reached equilibrium, which means the rate of the forward direction and the reverse directions equal each other, which means everybody gets locked into place, which means overall there's really nothing happening, right, in terms of entropy or increasing or decreasing it, because at that point they're locked in, nothing's really changing. So one way that we could use delta S to sort of figure out whether or not a reaction is going to be spontaneous or not is we want to calculate the delta S of the universe. And the delta S of the universe will be made up of two things: the delta S of the system, which sometimes is the delta S of the reaction, which is what you're kind of interested in or dealing with, and the delta S of the surroundings. So in order to use delta S, or the entropy, to determine whether or not a reaction is spontaneous, you do need to calculate the delta S of the universe. We're going to go through into here in just a second how we calculate each of those things. But you need to calculate both the system and the surroundings, add them together. And if you get something that is a positive value, then it will be a spontaneous process. Obviously, the opposite is true. If you get a negative value, then it will be a non-spontaneous process if you were to calculate it. So let's start with the system or the reaction and how we go about calculating them. So The entropy change of the system is basically your products minus your reactants. So if you're pretty much just given a reaction and not much else, and you're asked to calculate the entropy change, you would go to a table and you would look up the values, and you would take the products minus the reactants. You also need to make sure that you multiply by the coefficients. So again, if you had for C in the table 20 kilojoules, when you would go to C, and if this coefficient say was 2, C, you would need to take 2 times 20 for your value. So you do need to multiply by the coefficient. You want to add up all the entropy values from the table there for your products and subtract them from all the entropy values there in the table from your reactants. And again, in this situation, if you are a positive or negative value, it will not tell you whether or not a reaction is going to be spontaneous, but it will tell you, are you increasing or decreasing the entropy value in this case? So you can determine, is sort of the disorder increasing or decreasing. It will not necessarily tell you if the reaction is spontaneous because you did not calculate the universe. So why don't we try one here? I feel like I lost one on my handout, so I'll add it there. I think you have it on yours, maybe, which is CO2. So the CO2 is 213.6 joules per Kelvin per mole. All right, so take a moment, calculate the delta S. These are values, again, that you would find in a table. Okay, let's take a look. So once again, you would need to go to a thermodynamics table, which can be found in your book or most books in the back. Look up these values. So we're going to calculate our delta S here of our reaction, which is basically our system. We're going to take our products, which is 2 times the value of CO2, which is 213.6. We're then going to subtract it from our reactants, which we have 2 times the value of CO, which is 197.9. We're going to add that to our other reactant, which is oxygen here, which is 205. And we do all that good stuff. Looks like a minus 173.6 joules per Kelvin. Or if you want to leave it in joules, you can. In this case, we ended up with a negative value here for our delta S. That means that the disorder is increasing or decreasing. The order is increasing, the disorder is decreasing. And we can actually make a prediction based upon what we see in the actual equation to know whether or not we should have ended up with a negative value or a positive value. And we could do that by looking at the actual equation and how many gas molecules, for example. On the left-hand side here on the reactant side, that is 3 gas molecules. On the product side, we have 2 gas molecules. So we got 3 gas molecules flying around down to 2 gas molecules. So less gas molecules, that's going to increase the order, right? Less things flying around in your face. So that will increase the order in this case. And we should predict that we should end up with a negative value for our delta S of our reaction. So that is a way you could kind of make a prediction before you do the calculation. Make sure you didn't maybe mess up sort of the calculation. Won't help you with the number part, but the sign part should agree. Once again, this value here does not tell us whether or not this reaction is spontaneous or not. It just tells us really what's happening in terms of the order. It's increasing or decreasing based on the sign. Any questions on that calculation there? So once again, you can, as I said, look at a reaction and kind of determine based on things like how many gas molecules are produced. So if you are producing more gas molecules than you started with, you're going to be increasing the amount of disorder, and you would expect a positive value for S or delta S. If you do, as we just saw there in that particular example, end up with less gas molecules than you started with, that's going to create a little bit more order that's going to happen, and we would expect a negative value. If there's really kind of no net change in the gas molecules, It could be either way, but it'll be relatively small number. Again, you're not increasing that gas molecule. Remember, having gas molecules is a big jump in terms of the change in entropy, as they are flying around kind of crazily and a lot more disorder happening there. So the creation or not having it, less gas molecules, will make a big effect. So with that being said, if we had to predict here for the one on the bottom here, we expect the sign of the change in entropy to be positive or negative. I'm not sure. Let's see. We got on the left-hand side here, one gas molecule. Right-hand side, we have 0, right? Because those are solids. So that means that we have definitely increased the order in this case, right? We have no gas molecules. So we would expect the delta S here to be negative in this case, as the entropy is decreasing. The amount of disorder is decreasing. Any questions on that there? So that's a good thing to keep in mind as you're doing some of these problems. Take a look at the equation and make a pretty good prediction as to the sign you should get when you calculate something like the delta S. So let's talk a little bit about the surroundings then. The surroundings, which is basically everything outside of the system, can have an effect on our delta S of the surroundings. So one thing that could have an effect on it is actually the energy that's being released, or the delta H value. So on the left here, we have an exothermic process, which means our delta H in this case should be negative. And that's going to release the energy to the surroundings. On the right here, the energy is coming from the surroundings to the system, which means our delta H is going to be positive there. For our system, as it's going to absorb that energy. So when the heat here comes out, it's going to add energy to everybody in the surroundings, and they're going to do circles like this. But they're going to have more energy, which means they're going to start moving around probably faster, right? Which should increase or decrease the amount of disorder. Should increase the amount of disorder, right? They pick up more energy. We should see really the amount of disorder increase in this case. And that means that our delta S in this case will actually be a positive value for our surroundings, as it's going to pick up all that energy. Opposite maybe is a little bit true here. If we have our heat coming out of our surroundings, everybody in the surroundings is going to have a lot less energy, right? So they're going to be moving around a lot slower. Dramatic slow draw here, which means they're going to move slower, and that's going to create more order, right? Because they're not flying around as fast because of that. And we would expect the amount of disorder to decrease, or the amount of order to increase. You could choose whichever way you want to look at it, disorder or order. Just don't mix them up, I guess, as you're thinking. But here the disorder is going to decrease, which means, again, the order is increasing, and we should expect for our surroundings here our delta S to be negative. So the relationship is the delta S of the surroundings is proportional. That's what that little symbol is supposed to mean. Proportional to minus the delta H of the system. So what does that mean? It means if you have your delta H and you have your delta S of your surroundings, the delta S is minus basically the delta H of that. So if I have an exothermic reaction, my delta H is going to be negative. Negative and negative equals a positive value for our delta S of the surroundings. If I have an endothermic process, the delta H is going to be positive. Negative and a positive will give us a negative value there for our surroundings. So it's basically the opposite relationship as it gains that energy. Now, is the temperature of the surroundings important to whether or not you will actually see a change in entropy? What happens if my temperature of surroundings is like super high? Will the added energy make a big difference? It will not, because things are crazy to begin with, right? So don't do this at home. But, if you light up a match, for example, and you can feel the heat and energy coming off right in the room. Don't burn yourself, don't light matches, dangerous. But if you lit that same match and maybe put it in an oven at a very high temperature, again, do not do this at home. The heat coming off of the match, right, versus the heat in the oven, not going to make a very big difference of the overall heat that's in that oven, provided you turn it up pretty good. So the temperature of the surroundings to begin with does make a big difference in terms of whether or not you will maybe see a big entropy change, because if it's really high to begin with, you're going to have a lot of energy, a lot of disorder already. So that little bit of added that you put in there coming from the exothermic reaction is not going to make a big difference. But in sort of normal times, like the match in the room situation, you could feel the heat coming off. So it does make a difference, obviously, in that sort of situation. So under normal conditions, we will see this sort of exchange of heat versus the delta S of the surroundings. But again, if you should have a temperature of that surroundings, which is very high to begin with, then you might not see as big of a change in the entropy. So there's actually a formula for it, which looks very disjointed here. So we'll just kind of cross that out here. And we'll write up here, delta S of the surroundings is equal to minus delta H of the system or the reaction divided by our temperature, and I'm imagining it probably should be in Kelvin. Yeah. So make sure that that temperature is in Kelvin. That's a 273 addition, right? I think it's that number that you use when you do that. Now, this equation is used to calculate the delta S of the surroundings, and you should not confuse this equation with a version of this equation that we're going to see later, which what I'm saying probably makes absolutely no sense to you at this moment. But the difference will be actually in the negative here. So the negative does need to be included in this equation when you're calculating the delta S of the surroundings. Later on, we'll sort of derive an equation from a formula that looks exactly like this, but there's no negative. So just keep that in mind, the negative when you're doing that delta S of the surroundings. So this is how we would calculate the delta S of the surroundings. We would calculate the delta S of the system by taking our products minus the reactants. Then we could add both of those numbers together and we could calculate the delta S of the universe. And again, at that point, if you get a positive number, it will be a spontaneous process. And if you get a negative number, it'll be a non-spontaneous process. Any questions on any of that there? Well, then let's do it here. Here we go. A little bit of ammonia. N2 plus some H2. Delta H of this reaction is minus 92.6 kilojoules per mole. These are the delta S values you can find in a table. Calculate the delta S of the system, delta S of the surroundings, and determine whether or not this reaction is spontaneous at the classic 25 degrees Celsius temperature. Okay, let's take a look. So we're looking for a couple things. So first off, our delta S of our system, our reaction, whichever way you want to do it. It's going to be our delta S of our products minus the delta S of our reactants. And that is basically our final state minus our initial state. Once again, if they were not provided to you, you would need to go look them up in a table. So we do want to also take into account the coefficients when we do that. So that's going to get us here for our product side, 2 times 193 joules. That's going to take care of our products. Our reactants there, we're going to take basically 1 times our value there for our nitrogen. We will need to multiply by 3 for our hydrogen. And here we will end up with 2 times 193 minus 192 plus 3 times 131. Negative 199 joules in this case. Any questions on that there? Yes. I just say because, no, but sometimes sometimes technically the units won't cancel out. Technically the moles go away because these are moles, right? We're here. So you can't leave it if you like that. It may not match up again with this guy. So sometimes the units are a little wonky, if you will, in terms of how they properly cancel out. But so for me, I'm okay if you just leave it as joules in this case for delta S, but that's sort of the answer, I suppose. Other questions on that there? Now, in this case, we could make this prediction by looking at the equation. We have 4 gas molecules here, right? We have 2 gas molecules here. So we're going from 4 gas molecules to 2, which means we are creating more order. And we would expect, once again, to have the negative value there, which we do in this particular case. Now we could calculate our delta S of our surroundings here. And in this case, that's going to be negative our delta H of our reaction divided by our temperature in Kelvin. So a little 273 action on that there, a little 298. And here we're going to put in our value of delta H, which was given to us. That's going to be a negative times a negative 92.6. I'm going to multiply this by 1,000 to convert it into joules, because I know eventually I'm going to need to add it to that guy, so I am in the correct units. Here, if you left it in kilojoules and then added it to your joules on the other one, you're going to be off. So again, you got to watch those units as you're doing it. We're going to divide this by 298. We also want to remember that there is a negative in the formula, and this negative comes from the value that was given to us. So again, that's why we got the 2 negatives there. That's going to give us 92.6 times 1,000 divided by a 298 will get you about 311 joules. In this case, you would actually have joules per mole per Kelvin in this case. So in this case, we do have a positive value here for our surroundings, which also makes sense because this is a exothermic process, right? Which means that our system in this case is releasing that energy to the surroundings, should create a lot more disorder in the surroundings. And that's why we see a positive value for our surroundings. And it's a normal sort of temperature of 25 degrees. So, that is all makes sense. So these are things you want to think about. Obviously, if you left it in kilojoules, you would have something like 0.311. Yes. Divide by 1,000, the 92.6 in kilojoules, or no, because it's 92.6 kilojoules, and 1 kilojoule there would be 1,000 joules. So we'd be multiplying. But yeah, other questions on that? Yeah. So at this point, we can calculate the delta S of our universe, and that's going to be basically just adding those numbers together. We're going to take our delta S of our system, going to add it to our surroundings in this case, and that's going to get us, again, here, you want to make sure they are definitely in the same units. And since S is usually given in joules, it's not a bad choice to go into joules. And that's going to give us like a $112 joules here in terms of our delta S of our universe. First off, any question on the calculation part there? That would tell us, now that we calculated delta S of the universe, is this reaction spontaneous? It is, because our delta S of our universe is a positive value. So we have a positive value here for the universe. So it will be a spontaneous process. So this is a pretty good example of a reaction that is spontaneous, which means under these conditions, we would expect this reaction to take place. Also a good example of, if you don't use a catalyst, it's a forever type reaction. It's a very slow reaction, which is why people usually use catalysts for this reaction to speed it up. So again, spontaneity does not necessarily have anything to do with how fast or slow the reaction's happening. Question on any part of that, or delta S in general? Yeah. So let's talk about the third law of thermodynamics, which is the entropy of a perfect crystal is basically going to have a value of 0 at absolute 0 temperature. If you hit a perfect crystal, there's probably only one way to get a perfect crystal, right? So that would mean our number of microstates here would be 1. And as we saw earlier, that's going to take that to 0, which is why our entropy value here would be 0 to hit a nice perfect crystal, very, very ordered. As we transition from solid to liquid to gas, as we've been talking about, that's going to increase the entropy. These are also the transitions where we can have a certain amount of temperature change that occurs and a certain amount of energy that occurs with it. So for example, here, this is solid, this is liquid in this case, and this is gas. And the transition of these things occur as we go from, say, solid to liquid, right about there in that transition. Does that occur at the same temperature or different temperatures? Does occur at the same temperature. That's the normal melting point or freezing point of a substance, right? So if we're talking about water, for example, that would be 0 degrees Celsius, right? It happens exactly at that temperature, which means both phases are in equilibrium with each other at that temperature. Same thing down here as we go from liquid to gas. That occurs at the exact same temperature. That's like 100 degrees Celsius for water. That's the normal boiling point, right, of where that occurs. And at exactly 100 degrees, for example, you have both phases in equilibrium with each other. It's not until you get a little bit above or below those temperatures that you sort of fully transition into sort of the next phase. As you might remember, there's a certain amount of energy required to do that transition in terms of delta H, to go from solid to liquid or liquid back to solid. That is the delta H of fusion, right? And it is a positive value, obviously, as you go from solid to liquid. You have to put energy in to do so. And it's a negative value as you go from liquid back to solid, as you have to release that energy for them to come back into solid. For example, for something like water, that's something like 335 joules per gram, roughly 6.02 joules per mole, or kilojoules, I'm sorry, per mole. And that is the heat of fusion. Going one way or the other. There's also energy required to go from liquid to gas or gas back to liquid. That is the delta H of vaporization, right? And that for, say, something like water is roughly 2260 joules per gram, about 40.6 kilojoules per mole, give or take a kilojoule here or there. And that is the energy, again, required to just do nothing more than change the state of that matter, take it from at 0 degrees, for example, water, 0 degrees ice, to 0 degrees liquid water. So no movement of temperature, just actually changing the state of it. And again, it's going to be a positive number going in this direction, negative number going in that direction. So, by the way, if we were in the same state and changing the temperature, what do we use to calculate energy? So let's say I want to know how much energy is required to take liquid water from 5 degrees Celsius to 25 degrees Celsius. How would I calculate that? The specific heat equation, yeah. So that should be, I think, what you said there. So one version of it is Q is equal to ms delta T, right? Q is heat or energy. M is mass, right? S is the specific heat capacity. Some people use C, I think. Delta T is the change in temperature, right? So you use that when you're in the same phase, but you're changing temperatures. You use something like the heat of fusion or the heat of vaporization when you are at the same temperature, but changing phases, right? So that's what happens at those transition points. A total amount of energy you just add as you go up and down the hill here. We also have, as you can see here, entropy values for these things. So the delta S of fusion is the entropy change that occurs as you go from solid to liquid or liquid back to solid, and our delta S of vaporization is the entropy change that occurs as you're doing that transition as well. And it makes sense if we think about sort of our delta H sort of value as we go from solid to liquid. we should be increasing the amount of disorder, right? And we will end up with a positive value there for our delta S. And if we're going the opposite way, we should be decreasing the order or increasing the order as we go from liquid to solid, and we should end up with a negative value for our delta S of fusion. So that delta S for vaporization or fusion works the same way in terms of a sign. Depending on which way you're going in that transition, you'll get a positive or a negative value as you go through it. Any questions on that stuff there? All right, throw down from the past. Let's then talk about another thermodynamic value, which lets us use, thank goodness, a different letter, which is Gibbs free energy. And that is our delta G. And Gibbs free energy is much like the name, sounds like it is energy available to do some type of work and either work on the system or work from the system. As we just saw there, in a spontaneous process, we'll have our delta S of the universe that's going to be greater than 0. We will see, I don't know, maybe like 3 or 4 different ways to calculate delta G. And there's a few different ways that you can calculate delta G. The best piece of advice I could give you is pick the way that matches what's given to you. Yeah, so don't reinvent the wheel. So they give you some information, use the correct formula for that one. One way you can calculate is to take the delta G is equal to the delta H minus T delta S. That is our enthalpy. That is our temperature in Kelvin. That is our entropy. This, once again, is a situation where you have to watch units. Our delta H is probably going to be in kilojoules, and our entropy will be in joules. So again, here, you probably need to do a conversion one way or the other to get them both in the same units. Otherwise, again, you'll be off. Delta G is typically given in kilojoules. So I would say delta G and delta H are typically given in units of kilojoules, and delta S is typically given in units of joules. One of the nice things about delta G is you could actually use the value of delta G to determine whether or not a reaction will be spontaneous. So if you calculate the delta G and you get a negative value, that means that this reaction, the way it is written, is going to be spontaneous and head in the forward direction, basically from reactants to products. If you calculate the delta G and it is a positive value, that means the reaction is going to be non-spontaneous the way it is written, and it will be a spontaneous reaction if you reverse the reaction, and that's because your products become your reactants become your products. The sign changes, basically. Yeah, so it goes from being a positive value to a negative value in this case. And if you calculate delta G and it's equal to 0, the reaction is at equilibrium. So we could actually use delta G here to help us determine whether or not a reaction is spontaneous if we have enough information. So this is one of the formulas that you can use to calculate delta G, and this would be the formula you'd want to use if you have delta H or delta S given to you. Might as well plug it in here. And that would be one way that you could calculate it. Any questions on that there? I think we will lay it up there. It's probably a good place to stop, I think. All right. Couple reminders. Let's see. There's something happening, right? We are examining on Thursday at the very beginning. Yes. Like those happy students that were coming in at the end of our labs take their exam. We'll exam at the beginning is chapter 14, our favorite chapter ever, and 15. It is the test, yes, the test of tests, the test they write books about. So we'll take that, and then we will continue lecturing in lecture, and we'll get started kind of like normal, a little bit after 8-ish, and you'll have a couple hours or so. I do have your quizzes if you like those as well.